The moon is silent. There is no wind, no atmosphere, no sound. Its surface is covered in fine regolith, a powder formed over billions of years by constant micrometeorite impacts. Each grain is sharp, abrasive, and electrostatically charged. Above the horizon, Earth appears close enough to touch. In reality, it is nearly 400,000 kilometers away. On this surface, survival depends entirely on engineering. Today, we asked an artificial intelligence system to simulate whether a human could survive here for 72 hours, stranded, alone, and 2 kilometers from a lunar habitat. The simulation uses environmental measurements gathered from Apollo missions and modern lunar orbital data published by NASA. The subject is equipped with a modern extravehicular activity suit. Primary oxygen supply, 4 hours. Backup oxygen reserve, limited. Battery life, 6 hours under nominal thermal load. Distance to base, 2 kilometers across uneven terrain. Gravity on the moon is 1/6 that of Earth. Movement feels lighter, but balance becomes less intuitive. Momentum carries farther, recovery takes longer. With each step, regolith lifts slowly and settles without resistance. There is no air to slow it down. Without a suit, loss of consciousness would occur within approximately 10 to 15 seconds due to vacuum exposure. Irreversible damage would follow shortly after. Pressure, not temperature, is the first threat. In direct sunlight, the surface temperature can exceed 120 degrees Celsius. In shadow, it can drop below -170. The spacesuit compensates through internal thermal regulation, but only while power remains available. Radiation presents a more persistent risk. The moon has no magnetic field and no atmospheric shielding. Solar radiation and galactic cosmic rays continuously reach the surface. On Earth, our atmosphere absorbs most of this exposure. Here, nothing stands in the way. The AI begins calculating cumulative radiation dose from the first second of exposure. Hour 0. The astronaut begins moving toward the habitat. The terrain is uneven, filled with shallow craters and scattered rocks. 2 kilometers on flat ground might be manageable. Here, every incline adds metabolic cost. Walking speed is calculated at approximately 2 kilometers per hour under controlled pacing. Oxygen consumption remains stable during the first hour. After 2 hours, the AI projects survival probability at 96%, assuming no unexpected variables. The habitat remains visible, but distance perception on the moon is deceptive. With no atmosphere, there is no visual haze to provide scale. A stumble in low gravity does not feel dramatic, but falling incorrectly could damage suit integrity. The AI models suit puncture probability at a low but non-zero percentage. By hour 3, oxygen levels decline steadily but remain within safe margins. Breathing rate increases slightly due to physical exertion. The AI adjusts consumption projections accordingly. At hour 4, the primary oxygen tank reaches depletion. Backup oxygen activates automatically. Battery reserves fall below 50%. Thermal regulation continues, but with reduced redundancy. The AI recalculates survival probability, 81%. Fatigue becomes measurable. In reduced gravity, muscles work differently. Small terrain adjustments require greater concentration. Navigation errors become statistically more likely under cognitive strain. The astronaut climbs a shallow ridge. The habitat appears closer now, but still not immediate. Time is becoming the dominant factor. Then the AI introduces a variable, solar activity. The sun operates in cycles of magnetic instability. Solar flares release bursts of charged particles that travel through space. On Earth,
Most are deflected. On the Moon, they arrive unfiltered. The AI introduces a moderate solar flare event. Radiation exposure begins increasing above baseline. Cumulative dose rises faster. Under these flare conditions, the survival probability drops to 42% if no shielding is reached. The spacesuit alone cannot fully protect against a sustained solar radiation event. The astronaut continues forward. The Moon remains silent. There is no sky, only black space. There is no sound except the internal circulation of the suit. Isolation becomes a measurable variable. Psychological stress increases the likelihood of minor procedural errors, a miscalculation in direction, a slower than expected reaction. The AI incorporates human error probability into the model. Survival probability stabilizes at 74% under normal solar conditions without flare escalation. The habitat now occupies more of the horizon. Battery power continues declining. If sunlight remains constant, thermal systems operate within range, but if darkness approaches, conditions change dramatically. A lunar night lasts approximately 14 Earth days. Without sunlight, surface temperatures drop rapidly. Battery systems must compensate to maintain internal body temperature. If power fails during lunar night, core temperature